All right, so the last section of the standard model is all going to be about this classification chart and this particles of the standard model chart, which are both on your reference tables right here on page 3. We can start and we can see that at the top of our classification of matter chart, we have leptons and we have hadrons. So what are leptons? Well, we can see that nothing else branches off from leptons. So that tells us something. That tells us that they exist by themselves. So they're a fundamental particle. And they also do not act on the strong force. They have no strong interactions. They are fundamental particles and they're not made up of anything else, we say that they can exist in sort of they can exist by themselves. Actually, not all fundamental particles can exist by themselves. And what kinds of leptons can we have? Well, to see the kinds of leptons that we can have, we have to look to this section of the particles of the standard model chart. So we can see that the electron is a lepton. We also have muons, tauons, and 3 flavors of neutrinos: electrons neutrinos, muon neutrinos, and tau neutrinos. So those are all very similar. They're all considered neutrinos. And neutrinos are particles that are so small they pass through the Earth with no interactions. They have to build really fancy detectors to even see neutrinos. We said leptons were fundamental particles because they were at the bottom. They weren't made up of anything else. Another thing that we see at the bottom here are quarks. So quarks are also at the bottom. They're not made up of anything else. We can see specific kinds of quarks here on this side. So a quark is a fundamental particle, and they make up protons, neutrons, and other hadrons, right? Other things on this side. You might want to remember that protons and neutrons are specifically going to be made of up and down quarks, specifically. And we say they're fundamental because they're not made up of anything else, but because they have fractions of charge, normally we would say you can't be a fraction of an elementary charge, you can only be a whole number elementary charge. But they don't exist on their own, so that's why they have fractions of elementary charge. Then the following is true of leptons and quarks. For all particles, there is a corresponding antiparticle. And that antiparticle has the same mass but opposite charge. And we know it's an antiparticle because we'll see this line over symbol that usually meant average before. So again, if we look at this chart, we can see that we have the name up here. So the name of each of these, of this box, we're talking about an up. The name of this quark is a charm. The name of this quark is a top. The name of this lepton here is an electron, lepton. And then we have these symbols, right? So we have that C, we have that T for top, and then at the bottom we have charge. So an up quark has a charge of positive 2/3 and is represented with a letter U. A charm quark is represented with the letter C and has a charge of positive 2/3. So then we can think about antiparticles. An anti-up quark, right? We're not just going to write the U anymore to symbolize it. We're going to put a U with a bar on top of it. And that's going to have a charge of negative 2/3 elementary charges instead, but the same mass as whatever an up quark had. And this is actually noted that there is an antiparticle right here. It doesn't tell you that it's got the same mass and opposite charge. That's something that you just got to remember. All right, and then we can also see that if we look at hadrons specifically, hadrons are broken up into baryons and they're broken up into mesons. And a baryon is going to be composed of 3 quarks, and a meson is going to be composed of a quark or an antiquark. Hadrons were broken up into 2 groups. We got baryons and mesons. A baryon is composed of 3 quarks, and a meson is composed of a quark and an antiquark. Now, you can have an antimeson because you already have an antiparticle flowing around here. But because a baryon normally is just 3 quarks, we also sometimes say that an antibaryon is 3 antiquarks. But we can do some example questions related to these ideas. A baryon may have a charge of, now a baryon is something that exists by itself, so that's got to have a whole number elementary charge. We got another one. An atom is made up of 3 neutrons, or 3 protons and 4 neutrons. How many quarks are there? So there's a piece of information to answer this question that I'm going to add up here, and that is that protons and neutrons are both baryons. So knowing that is going to help us here because we know in one baryon we have 3 quarks. And if I have 4 neutrons and 3 protons, then I have 7 baryons, which means I have 7 times 3 or 21 total quarks. Because each of those baryons, one baryon has 3 quarks in it. So if I have 7 baryons, I have 7 times 3 for 21 quarks. To go through these classifications, I'm going to want to have this part of my reference table is open, and then so I can make sense of what kinds of particles I'm looking at, and then what does that mean I have. So in that first one, I have a top, and a bottom. So I have 2 tops and 1 bottom, and all of those things were quarks, so I have 3 quarks. And if I have 3 quarks, what kind of particle am I? Well, 3 quarks is a baryon. Now, if I just have an electron is right there. What kind of particle is that? That's a lepton. So I can call that a lepton. I can also be filling in the charges here. An electron is a lepton with a -1 elementary charge. That top, bottom, so I have the total, I have 2/3 plus 2/3 minus 1/3. So that's 2 plus 2 minus 1. So that's 4 minus 1 is 3/3, which is the same thing as 3 divided by 3 over 1. So I have +1 elementary charge there. Now if I have an up quark and an anti-up quark, that line on the top means an anti-up quark. That means I'm talking about what kind of particle? Well, I have a quark and an anti-quark, so I'm talking about a meson. And an anti-quark has the opposite charge as its corresponding particle. So that means that those two things have opposite charge, and I have to end up with 0. Now, antineutrino, that's going to be one of these things down here, but the anti-version of it. So what kind of particle is that going to be? Well, my neutrinos are all leptons, and all of my neutrinos have 0 elementary charge. So an antineutrino also has to have 0 elementary charge. S by itself, what does that S mean? Well, S there is strange, so that's just a quark, and it's got a charge of -1/3 elementary charges. Now I have all three. I have an anti-up, an anti-up, and an anti-down. So what do I have? Well, if I had 3 quarks, I would have a baryon. But I have 3 antiquarks, so instead of having a baryon, I have an antibaryon. And an up quark had a charge of +2/3, so an anti-up quark has a charge of -2/3 elementary charges. That's plus a -2/3 elementary charges. And then down, that's normally -1/3, but in this case, it's an anti-down. So I'm going to add a +1/3 elementary charges. So I have -4 plus 1, or -3 divided by 3 elementary charges, or just -1 elementary charge there for my antibaryon. All right, I hope to be back soon. Thank you again for tuning in.